Welcome back to lecture 7 of our statistics series for ENIGMA-U. Today, we are going to be talking about the T statistic. The T statistic is like the Z statistic that we've introduced before, but we use it under slightly different circumstances. And we're going to talk about when it is appropriate to use the T statistic, how it's the same as the Z, and how it's a little bit different. Okay, this is just a cute little comic that shows some of the dramatization of z-tests in the media, or how statistical results can be a little bit misleading if you don't understand how they're used or their definitions or context. Here it's saying, there's this person that's saying, scientists, we hear that jelly beans cause acne, you should investigate. And they're saying we found no link between jelly beans and acne. But then they're going to look at the certain colors. I heard it's only a certain color that causes it. Scientists, but Minecraft, they find no link between gray, tan, cyan, green, gray, tan, cyan, mauve, beige, lilac, black, peach, and orange. And all of these, they find no link between them, but there is a slight link between green jelly beans and acne. But the only statistic that they give is that the p-value is less than 0.05. Which, as you remember, p-values are not statistical facts. They are not saying that there's a huge effect size. It doesn't tell us anything about the confidence interval. It's just telling us that this merits further research, but the news will often dramatize it and say, green jelly beans linked to acne, 95% confidence, only 5% chance of coincidence, which, as we know, is not what this p-value means. So we're going to look at some other ways that we can use hypothesis testing with a slightly different test statistic to tell us some different things that might be more helpful than a p-value. So today, the tools that we're going to need, as per usual, are these symbols, the population and sample means, as well as population and sample standard deviations. A reminder, this sigma sub m is the standard error of the mean, which, if you need a refresher on that, we're going to talk a little bit about it, but go back to a couple lectures ago. And then n is our sample size. Then we're going to use these formulas and these concepts. So really quick review slides. The one thing we're going to review is the one sample z-test. This is the hypothesis test that we learned at the beginning of hypothesis testing units using this z statistic here. As a reminder, the z-test is a statistical procedure that allows us as researchers to use a sample mean to test a hypothesis about an unknown population mean based on these following things: that the sample mean is expected to approximate a population mean. Those things are going to be about the same. The standard error is the measure of the difference that is expected to occur between the sample and the population means. And because of these two things, we can use the z-score to quantify our inferences about the population by comparing the differences between the means in relation to what that difference is expected to be, basically. And in bold here, the goal of any hypothesis test in general, which we're going to carry through our lecture today, is to determine whether the obtained difference between our data and our hypothesis is significantly greater than what we would expect just from chance or sampling error. However, you might have wondered as we've, let me make this a little smaller. I don't know if I can. Okay, that'll be fine. You might have wondered as we have gone through our lectures, when we are calculating z statistics and we're putting it in the formula, it requires that we know the standard deviation of the population, not just the sample. And the kind of paradox with that is the whole purpose of a hypothesis test is to gain knowledge about an unknown population. So we take a sample and we do some data collection with that so that we don't have to collect data about the total population. And so using a z-score for a hypothesis test usually requires us to know more information than we have available. The population is unknown, so we don't usually know the standard deviation of our population. However, we need that information if we want to be able to compute our z-score to find out what the standard deviation of the population might be. So it's just kind of this circular reasoning paradox. However, The solution to this is, instead of using the population standard deviation, let's calculate the estimated standard error using an unbiased, remember, we make things unbiased by using degrees of freedom, an unbiased sample standard deviation. We're going to use the sample standard deviation, which we know, to estimate what we think our standard error will be. And that, my friends, is where the t-statistic comes in. So we use the t-statistic to test our hypotheses about an unknown population when we don't know the value of the population standard deviation. If you don't know that information, you can't do a z-statistic, so we have to do a t-statistic. The formula for the t-statistic is basically exactly the same as the z-score formula. The numerator is exactly the same, but the denominator is different. Instead of using the population standard deviation, which is the denominator of our z-statistic, the t-score uses, or t-statistic uses the estimated standard error in the denominator instead, which we're going to learn the formula for in a second. So if we want to determine how well a t-statistic can approximate a z-score, even without some information about our population, we need to first determine how well the sample standard deviation approximates the population standard deviation, because that's the only difference between our t and z statistics. So, quick reminder, degrees of freedom describes the number of scores in a sample that are independent and free to vary. We talked about this a couple lectures ago, where we have established that the degrees of freedom in any given distribution is going to be n, or the sample size, minus 1. Because once all of the scores are determined except for one, then you can calculate that last one. So n minus 1 scores are independent and free to vary. And we use this in the denominator of our formulas instead of n when we want to make sure, when we're making an estimate, but we want to make sure that it's an unbiased estimate. So that's what we're doing here. The sample standard deviation formula has two parts. Number one, or the denominator, which we just talked about, is the degrees of freedom here to make it unbiased. And the numerator is what we call the sum of squares, or in other words, we take the difference of every value from the sample mean, we square it, and we add them together. That's what you'll see it as SS, capital S, capital S. That is what that means. Okay, let's talk a little, now that we know how to calculate a t-score or a t-statistic, we need to talk about the t-distribution and how it's a little bit different from our z-distribution. So the t-distribution is the complete set of t-values computed for every possible random sample for a specific sample size, n, or a specific number of degrees of freedom, n minus 1. In some ways, the t-distribution is very similar to the z-distribution in that it approximates the shape of a normal distribution. It's bell-shaped, symmetrical, the mean is at 0. However, t-distributions are more variable than a normal distribution, which just means their shape is going to be a little bit flatter and a little bit more spread out. And actually, the exact shape of a t-distribution is going to change with the degrees of freedom, or in other words, it's going to change based on your sample size. Let's look a little bit into that here. So here is our normal distribution in gray, or in other words, this is what the t-distribution would look like if your degrees of freedom were infinity, if your sample size was approaching infinity, right? The reason that the t-distribution here, you can see as your sample size or your degrees of freedom get smaller and smaller, the t-distribution gets flatter and a little bit wider. The reason for this, is actually because of the formulas that we use to calculate our t-statistic versus the formula that we use to calculate our z-statistic. For both z and t statistics, the numerator is m minus, so the mean of the sample minus the mean of the population. That's the numerator in both of them, exactly the same. And that can take on different values in both of them because the sample mean is going to change from sample to sample, right? However, in your z-statistic, your denominator is the standard deviation of the population. And if you're taking all of your samples from the same population, that denominator should stay constant. So only the numerator changes in your z-statistic from sample to sample. However, in your t-statistic, The denominator of the t statistic is the estimated standard error of the sample. So the t statistic, the numerator, and the denominator are going to change from sample to sample, which just means that you're going to have far more variability in your distribution. And that is shown here because the distribution is getting flatter and wider. However, important to note that as your degrees of freedom increases or approach infinity, the t distribution approaches a normal curve as well. The last thing we're going to say before we leave this page is something else to look at is why all the tails are not in the same place. So the normal distribution, you can see the tail is lower than the tails of the t distributions. The reason for this is, in general, t distributions are going to have more extreme values than z distributions. Because there's more variability, like we were just talking about, and because we used the standard deviation of the sample to estimate that denominator value. Essentially what that means is that the tails of the t distributions are going to be elevated relative to a z distribution or a normal distribution. Why is this important for us? Practically, that means for any given alpha level, remember where we're setting our critical zone on the edges here of the tails. For any given alpha level, the critical value of t is going to be higher than the critical value of z, which just means that the t-test is a little bit less powerful than a z-test. Or in other words, for any alpha level, your t-score needs to be higher than your z-score would need to be in order to reject the null hypothesis or have a score that ends up in that critical zone. And we'll look at some examples of that in a second. So finally, I know you've been wondering, this is what a unit normal table can look like. This is specifically the unit normal table for figuring out your t critical values, but the z critical table looks pretty similar to this. But the way that you use this is once you have your degrees of freedom of your sample and you have set your alpha level, your alpha value, you can figure out using this table what your critical value will be for your t-score. The nice thing is you have an option if you're using a one-tailed or a two-tailed test, which is kind of nice. What you would do is you would go here, you would find your degrees of freedom on this side, you would trace it over to whatever alpha value you have, and whatever number you land on, that's going to be your t critical value. For example, if your degrees of freedom were 3, if you had, for example, a sample size of 4, your degrees of freedom would be 4 minus 1, which is 3. 3. And if you decided that you wanted an alpha value, a two-tailed alpha of 0.1, then you would say, okay, 3, drag it over here to 0.1, and your t critical value would be plus or minus 2.353. You can see that right here. A t distribution with degrees of freedom of 3, and you have a two-tailed alpha of 0.1. That means that 5% is in each of your tails. So the proportion in one tail is 0.05. The proportion in the two tails combined is going to be 0.1. So your t critical value here, the edge of your critical zone, is going to be either positive or negative 2.353. And we'll come back to this when we do some practices. So we talked about a one sample z-test. Now let's talk about a one sample t-test. A situation in which you would use a one sample t-test instead of a z-test, is when you begin with a population with an unknown mean and an unknown standard deviation, and we want to compare it to our sample. In other words, a one sample t-test is going to compare the mean score that you find in your sample to a hypothetically assumed value. And there are typically the hypothetically assumed value that you're testing is going to be the population mean or some other like theoretically assumed value that we've come up with. And there are some specific applications here. So one application of one sample t-test is when you're testing your sample mean against a predefined population mean. For example, let's say you were a researcher and you wanted to disprove that the average age of retirement, for example, in the United States, is 65. What you would do is you would draw a representative sample of people entering retirement and say that you found out that, and then you would collect their ages. Then you would run a one sample t-test comparing the mean of your sample, let's say it was 63, to the predefined population mean of 65, because that's what we assume, or that's what we have previously defined as the mean retirement age in the United States. And then this t-test would analyze whether the difference we found in our sample of 63 to 65 is just due to chance, or if our sample mean differs systematically from the hypothesized mean of the population. Another application would be testing your sample mean against an expected population mean, which is similar, but the example I usually give for this one is if you are tossing a coin and you notice that it's not completely random, you would measure the results of your coin tosses, and then you would assign one side a 0, one side a 1, like we've done before, and then you would compare the mean of your sample of coin tosses to the expected mean of 0.5 by the laws of chance. That's another way you would use a t-test, because the expected mean is 0.5 in that situation. Another one is when you're testing a sample mean against a population mean that's derived from like common sense or largely agreed upon expectations. For example, let's just say you grew up in a village, you suspect that the IQ of your village is higher than the general IQ of the public. You would collect some data, you would compare the sample IQ of your village against what we say is the common sense or agreed upon general IQ of the population, which is 100. And lastly, you can use a one sample t-test to test the results of a replicated experiment against those of the original study. And in this case, your sample mean is going to be your study, the replicated study, I guess, that you did yourself. And the hypothesized mean, is just going to be the previously reported mean score from the original study. So those are just some examples of times when you would use a t-test instead of a z-test. In general, you use a t-test when your null hypothesis is obtained from a theory, a logical prediction, or just wishful thinking, when you don't know what that mean is. Let's talk a little bit about some of the steps of the one sample t-test. So the null hypothesis, which is always our first step in hypothesis testing, is to state our hypotheses, right? The null hypothesis is going to state that the treatment has no effect, or in other words, your treated sample will not differ from the untreated hypothesized population mean. The alternative hypothesis, as we talked about before, says that there is going to be a difference. Remember, we don't need to specify a direction. The sample, so then we're going to calculate our t-value. You're going to get the mean sample from your, or the sample mean from your sample data. Your population mean is going to be hypothesized from your null hypothesis. It's that thing that you're just assuming, you're wishing, logical thinking. And then your estimated standard error from the sample is also going to be computed from the sample data. In this way, just like our z statistic, the t statistic also forms a ratio. The difference between the mean and your hypothesized mean, and how much of that is based on chance, essentially, by putting it over how much difference is reasonable to expect between those two. And when your observed t-value is much larger than we expected, we get a large t statistic, we reject the null hypothesis, and we conclude that there was a treatment effect. So a lot of this will probably sound very, very familiar because it's a lot of what we did with the z-test. Let's talk about some of the factors that affect what our t-value is going to be. The two big ones are that it's going to be affected by the size of the sample, n, and the magnitude of the sample standard deviation. So obviously, because the estimated standard error is in the denominator. As your standard error increases, your t-value is going to decrease, and vice versa. So generally, this estimated standard error is going to be what changes your t-value. And here are the two things that affect estimated standard error. If you have a larger standard deviation in your population, then your standard error is going to be larger, which means your t-value is going to be smaller. So larger, so in summary, larger sample standard deviation means smaller t-value. If you have a larger n value, a larger sample size, you're going to have a smaller standard error, which means you're going to have a larger t-value. So in summary, if you have a bigger population, a bigger sample size, you're going to have a bigger t-value. So let's go through the steps, because right after this, we're going to do some practice to round out this lecture. So step 1, like we said, state the hypotheses, select the alpha level. We know what this is. The note here that I will say is, although in a one sample t-test, the actual value of your population mean is unknown, you can still form a logical hypothesis in regards to the value of the mean. You can either say in the null hypothesis that your sample mean is going to be the same as your expected or hypothesized mean, population mean. An alternative is that your sample mean is going to be different than your hypothesized population mean that you don't actually know, remember, because if you knew it, we would do a z-test. Okay, the second step is going to use that critical table that I showed you here, this one here, to determine our t critical values. And then we're going to calculate our test statistic. The 3 things we need to do to calculate a test statistic are, number 1, calculate the sample standard deviation, S here. Then 2, once you have that, you're going to plug it in to your estimated standard error formula, solve for that. And then you're going to plug this into your t statistic value and solve for that. And then once you have your t statistic, you're going to compare it, see if that t statistic falls inside or outside the critical region, and make a decision regarding your null hypothesis. I would recommend to take a screenshot of these formulas or something, or write them down, because we're going to be doing some practice in the next couple slides, and it will be helpful to have them. So we're going to do one example together, and then we're going to do 2 practice ones that I'm going to have you pause and do them by yourself, and then we'll check together. So this first example says, based on previous research suggesting that infants, even newborns, prefer to look at attractive faces compared to less attractive faces, a recent study was conducted in which infants from 1 to 6 days old were shown 2 photographs of women's faces. Previously, a group of adults had rated one of the faces as significantly more attractive than the other. The babies were positioned in front of the screen, the photographs were presented to them, and the pair of faces remained on the screen until the baby accumulated a total of 20 seconds looking at one or the other, a combined 20 seconds between the 2 of them. And then the number of seconds looking at the attractive face was recorded for each infant. The study used a sample size of 9, and the data produced a sample mean of 13 seconds for the attractive face. And your SS value, it's really nice that they give you this sum of squares value is 72. They won't always do this, but here we will, because we care much more about, for the purposes of these lectures, we care much more about conceptual and understanding the basis of statistics than if you can just plug it into a formula. So I have some crazy hair going on right now. Okay, so step 1, we're going to state our hypotheses and select an alpha level. Our null hypothesis is going to be that the infants are going to have no preference for either face. There's going to be no difference between the time that they looked at the attractive and the less attractive face, which means that our mean should have been 10 seconds for the attractive face, because that's exactly half and half. Our alternative hypothesis is that the sample mean is not 10 seconds, that they spent more time looking at one face than the other. And we're just going to decide, based on our delving into the research, that an appropriate alpha value is a 2-tailed 0.05. So then we would calculate our degrees of freedom, which here is n-1, 9-1 equals 8. We would use the degrees of freedom and a 2-tailed alpha of 0.05 to calculate the t critical value. Here, what we would do is we would find 8 in your degrees of freedom, And then you would say, we want the proportion in the two tails combined to be 0.5. So we would take this and our degrees of freedom, and that gives us a t critical value of plus or minus 2.306. Then we're going to plug all of our values in to get our test statistics. So remember, first step, calculate, like we said here, calculate your sample standard deviation. So SS is 72, degrees of freedom is 8, our sample standard deviation is 3. We're going to plug that bad boy into our standard error formula along with our sample size. So we get a standard error, an estimated standard error of 1. We're going to plug that value into our t statistic along with the means of the sample and the expected mean from our null hypothesis. Remember, 10 seconds, because that's what our population mean in a t-test is. It's whatever you hypothesize based on your null hypothesis. And we find that our t-value is 3. Now we got to make a decision. Since 3 is more than 2.306, that means it's going to be, it would be somewhere in here, right? In our upper tail. That means it's in the critical zone, which means that we are going to reject the null hypothesis, which essentially means that there is a difference in the amount of time that babies spend looking at attractive faces versus non-attractive faces, that they do show a preference. Even though we didn't talk about that in our null hypothesis, since we see that our mean is 13 seconds for the attractive face, our data says that babies have a statistically significant preference for looking at the attractive face. However, we don't have an effect size or confidence interval, but we'll talk about that in a second. Okay, now for the next little bit, I'm just going to have you do a couple of practices. I'm going to pause right here. Maybe we'll go through this together. Actually, no, I'll let you read this on your own and then go through each one of these. You're going to calculate or state the hypotheses, locate the critical region, calculate the t statistic, and make a decision. Since you might not have access to a t critical value table, I will tell you that the t critical value is plus or minus 2.797. That's the value for this one. So I'm going to take a brief pause, and then we're going to come back and go over these together. Okay, so let's go through this together. So this neuropsychologist suspects that his patients with multiple sclerosis are going to take longer to complete a processing speed task than healthy people. From his previous research, he's saying that the task takes an average of 40 seconds for healthy people. Let's talk about what his hypotheses would be. So, the null hypothesis here is that the mean of the sample is going to be equal to the mean of the population. So what that means in this context is that the sample mean for the patients with multiple sclerosis will be 40 seconds because that is the hypothesized population mean for the healthy participants as well, 40 seconds. The alternative hypothesis is just that the sample mean will not be 40 seconds. We've already talked about how the degrees of freedom, since there's 25 patients, is going to be 24. The t critical is plus or minus 2.797, which we talked about. Let's now calculate our t statistic. I'm not going to go through it with you. I'm just going to show you the answers. The t observed value is going to be 4.345. I think you have all the information that you need for that. Yeah, awesome. You didn't need the sum of squares here because they gave you the standard deviation. S equals 8.4, if there was some confusion about that. And then so our t critical value is 2.797. Our t observed is 4.345. We're going to reject the null hypothesis because our t observed is bigger or is outside the range of our t critical, which means that his hypothesis here was correct, that patients with multiple sclerosis do take longer to complete a processing speed task than healthy people. Okay, awesome. We're going to do one more practice, and then we are going to talk about some assumptions, and then we're going to take a break. So again, I'm going to take a quick pause, and then we're going to come back and do this together. I just actually realized that I never gave you your t critical value. The t critical value is 1.684 plus or minus. So Feel free to take a pause. I'm going to just sit here for 5 seconds while you pause, and then we're going to continue going. Okay, let's keep going. So this researcher is looking at, does caring for a person with Alzheimer's disease have an effect on the caregiver? The hypothesis is that caregivers suffer from elevated levels of depression. Okay, so the hypothesis, and this was a tricky one too, is that he was saying, or in our description here, we're saying that we're going to use a one-tailed test, not a two-tailed test, which means that our hypothesis will be directional. So our null hypothesis is that the sample mean of depression scores for caregivers is going to be less than or equal to the population mean for healthy people, which they said here, scores at or above 25 are considered to reflect clinically significant levels of depression. So this would be that the sample mean is going to be less than or equal to 25. The alternative hypothesis is that the sample mean of these caregivers for their depression scores is going to be more than 25. Critical region we talked about, since the mean BDI score was calculated for 36, or since the BDI scores were taken for 36 caregivers, our degrees of freedom is 35, our T-crit is 1.684. The T statistic that you should have gotten is 2.258, which means that we're going to reject the null hypothesis because 2.258 is more than 1.684, which means that it is in the critical zone. Okay, really quickly, I want to just go over some assumptions that we make when we do a one sample t-test. They're pretty much exactly the same as the assumptions that we make when we're doing a one sample z-test. Just a reminder, we assume that the dependent variable was measured on an interval or ratio scale, not nominal or ordinal, that we used random sampling to create our sample, that we collected our dependent variable using independent observations. There was no relation, or the collection of one variable did not affect the collection of the next. We have homogeneity of variance, which means the standard deviation for our sample is the same as that of the comparison population. And that's something that we assume, right? Because we're using an estimated standard error. And then the population sampled should have a normal distribution. Okay, and with that, we're going to take a brief break, and then we're going to come back and we're going to talk a little bit more about what types of effect sizes and confidence intervals we should report with t-tests.